equation purely driven by geometry. And it's a very simple direct derivation which follows from only one fact, that when space-time is inhomogeneous, then this is where we come to. Only some additional part of interpretation we had done was only identification of this quantity with energy momentum. The rest all was geometry driven. And this identification we have justified first that yes, whatever this quantity is, it is conserved because it is required by the equation itself. And this we said that this should be something which is the physical parameter or property which is shared by everything that physically exists. And it is the presence of that entity makes the space-time inhomogeneous for all particles. And that's why it said that we identify with energy momentum, and you have so that's how it most naturally came as the Einstein equation. So as a matter of fact, we could have as well said, another way of looking at this is that we initially made no appeal that we wanted equation of motion for gravitation. We were simply probing what happens if space-time is inhomogeneous. And we ran here. Another way of looking at it, I could have said that suppose I want an equation of motion for universal force. By universal force, the force which affects everything which physically exists. It links to everything. And that they said that all things could be categorized into two things, which have mass or which have no mass. Massless and massy particles. So to be universal, the force which is true for it links to both massive as well as massless particles is linkage to the massless particle, which tells us that the force can only be described by the space-time curvature. Because the massless particle in no other way can feel any force. So you come to that there has to be the force has to be described by the space-time curvature, and then once you have that, then this all follows. And then of course you will say, so now you have so gravity is described by the curved space-time, and now you ask the question, what is the motion under gravity? So it is the same question to ask, what is the motion of a particle, a free particle? And you immediately say, is the motion is straight line. That's of course a straight line related to. Now here I have, instead of a flat space, I have a curved space. And what has curved the space? Gravity has curved the space. Or the matter which produces gravity has curved the space. So now you say, and it's curved the space-time. It is curved the space-time, that means all particles follow the same trajectories. Like in absence of force, all particles follow the same trajectory. The same thing here. So what you have to say, motion under gravity is now that straight line in the curved space. And that is given this beautiful name called the geodesics. So the particles under gravity, the motion under gravity is the geodesics of the curved space-time. Now, this, or which are other way of knowledge. And how do you define the geodesics? How do you define the straight line? So generally there are two equivalent definitions for straight line. One you call it a more mechanical thing, saying the extremal distance. Shortest or maximum, whatever. Another this thing is, it is an orthoparallel curve, a geometric definition. The curve which is parallel to itself. So its tangent is constant. It's an autoparallel curve. So now you in curved space-time you define have your geodesics. So the picture then comes about that gravity no longer remains. So why I say that Newton's second law doesn't apply for gravity. In our conventional sense, it did not make sense that you had m was equal to f. This is meaningless when m equal to 0. I want to include m equal to 0 particles in my framework because the gravity is universal. It should affect, link to everything, massive as well as massless particles. So that has no meaning. Now, once you say that if you, when you come to this, that of a geodesics, geodesics is a motion under no force. It's a property of the space-time, whether it is a flat or whether it is a curve. So now, for the curved space-time, the force of gravity has now become the part of the space-time structure. It's in the geometry of the space-time. So hence gravity no longer remains, or in general relativity, gravity is not an external force. It is a force which is sitting in the space-time geometry itself. So you are going to, so you will have a geodetic equation similar to what you have on your mx double dot equal to 0 for the flat space motion. Here you will have a similar sort of thing to say. So let's say u dot equal to 0. And now of course I will in curved space, these derivative things I should define which are valid in the curved space. So you have this, so your u dot A is UA covariant derivative V along that. It's a tangent. So if you carry the things this. So that's the acceleration, the 4 acceleration you will get. And the 4 acceleration 0. M here is meaningless. You don't have to. So it's a u dot equal to 0. So like, so as a matter of fact, equations. So you will say u dot 0 for flat space, for the free motion. U dot equal to 0 in curved space. This is the motion under gravity. So what another way of to say is motion under no force is analogous to motion under gravity, except that in the former case the space is flat, in the later case the space is curved. So you come from the no force to the universal force, the thing, from space being flat or the space being curved. And the motion is always described by geodesics or orthoparallel curves of the space-time, which makes no reference to the mass of the particle. So what in the unsolvable problem we had to justify why the inertial mass should be equal to the gravitational mass in the Newtonian case, to show that the acceleration due to gravity is independent of mass. Then you have to justify this. So this is what your principal equivalence said. Now I said we don't need to address this question at all, because this question is relevant only follows from this, from the Newton's second law. But the Newton's second law does not apply to a universal force. So it does not apply to Einsteinian gravity. Since it does not apply to Einsteinian gravity, this question doesn't arise. However, we have to take into consideration what is required by the principle of equivalence. And that is to say that locally gravity should be removable. In your famous Einstein's freely falling lift, if you let yourself freely fall with the lift, which nobody in one's right mind will actually do it, so let's all. And Einstein invented this beautiful new laboratory called the thought experiments. So you do a thought experiment and you say everything falls with the same acceleration. Then in that, if I leave the chalk piece here, that will stay where relative to my hand wherever I leave it. Because my hand as well as the chalk piece, they both all fall with the same acceleration. So what, in other way to say, the locally gravitational force should be removable. That's the. So this is another very distinctive feature of gravity. In no other force you ask this kind of a question, that the force is zero locally but otherwise non-zero. The other reason for that is to say this liberty is offered to us, but simply this thing also we could have argued this. If your field is a vector field, then it does not give you this possibility. If a vector field is zero at one point, it will be zero everywhere. You can't have. So where do you get the liberty? You ought to get to a higher order thing. If you come to a tensor field, that gives us the liberty by tensor fields. So here what we are going to say, the force is generally, so let's say, the force you define as the gradient, right? Or which I will say is the first derivative. It will know the first derivative, right? So it's so long if you have a vector field, only way your force will be a gradient. You will involve only the first derivative. If it is zero at one point, then it's zero everywhere. You can't do much. However, if the force, the term force I am using in one sense, it's more in a normative sense. And that would be where it involves both the first as well as the second derivative. Then it gives you, so that means the field, that's probably better calling the field. Okay? Field involves both first derivative and second derivative. Now this gives me a possibility that locally at a point, first derivative may vanish. I can choose a coordinate system in which first derivative vanishes. But the second derivative will not. Hence, the entity, the field which I have, which involves both, this will be non-zero even when the first derivative is locally zero. So first derivative is is locally 0. Second derivative will still be non-zero. And that will give me the thing that the field as a whole still remains intact. The force which we appear, you measure in your, where is that? Here in the geodesic thing. So the terms in geodesics, what you have, it involves the first derivatives. Your Christoffel symbols are defined as the first derivative of the metric. The metric is the potential, so you have a first derivative for the metric. So, which you could say, which you can locally assume to be 0. What does that mean? Practically what we are saying is that this being possible means we can locally remove the gravitational force as we understand in the Newtonian way, in the equation of motion. However, the second derivative is non-zero, so that true measure of the gravitational force, which is sitting in Riemann curvature, which is a function of first and second derivatives, it is square of the first and then, that will continue to be non-zero, even when the first derivative is 0. Now, when we say the first derivative could be chosen to be 0, this is equivalent, that means locally I can choose an inertial, I can define an inertial frame. So that this allows me locally, we can define an inertial frame. Inertial frame which is free of all forces, or which means the locally gravity can be removed. Now, so what it means was that in the neighborhood of a point, first derivative can be made 0. This should be the property of your spacetime. So it tells me this. So I have a Riemann space as spacetime. At any given point, I can choose a tangent plane. You have a curved spacetime like the Earth. At a given point, you can choose a tangent plane where your Euclidean geometry holds good. Space is flat. That's precisely what we do here. We do really know that we are sitting on a curved sphere, but local, all my land measurements I still use the Euclidean geometry, simply because the locally it's a tangent plane I can define. So the Riemann space property of defining a tangent space at any point. This could be done at any point. Nothing to do whether gravity has to be weak or strong. It could be done right at a stupid black hole. No problem with that. So you could though. At any point you can define a your tangent space. That means you can define an inertial frame. And that means you incorporate principle of equivalence. So this is how the principle of equivalence is automatically incorporated in the curved spacetime. The space-time geometry being Riemannian ensures that the principle of equivalence is automatically. So now, when we say that I'm testing the principle of equivalence, what I'm really testing is whether the particle is moving along the geodesic or not. So, in other way, when we are calling that I'm testing mi equal to mz to the order of 10 to minus 12, 14 or something, what I'm doing is, if real interpretation is, I'm testing that the particle is following geodesic. So that is how beautifully the principle of equivalence gets incorporated in the space-time geometry automatically without you asking for you. Here I want to say, where is it sitting? How it is incorporated? And that's what we did. Now the next question I said was something similar we should also do. Yeah, is about the self-interaction. So we know sweep 1, the gravity is self-interacting. Now, why should it be self-interactive? It's self-interactive because it is universal, which means that energy in any form must gravitate. Must interact gravitationally. Right? We know all physical fields have energy. So, you have an electric field, you have the energy density as half E square, you know. That is the energy density force. Similarly, gravity must also have gravitational field energy. So gravitational field has energy. This must also interact gravitationally. So that is the self-interaction. So you have, say, a mass point which produces the gravitational field, say, let's say, what will you call it? I'll say some FG, right? But now you would say, but the gravitational field has energy spread all over the space, that must also interact. So that must also integrate if you want to say this. So that should have some energy density of half g square, like half g square here. So now that should also, in addition to the mass, that should also produce gravity. So that's what the self-interaction is. And the question what he suggested that one indication of it with the gravity is self-interactive is because the Einstein equation is non-linear. And where is that non-linearity coming from? The non-linearity is coming from here. That it involves the square of the first derivatives should get involved. And this, of course, we see this in the Riemann curvature. Riemann curvature has both square of the first derivative and that second derivative. It is the square of the first derivative, that's where your self-interaction is sitting. Right? But we ought to see this. And the problem I had was that I do not explicitly see in any textbook being revealed to people that where is this self-interaction going. Because the gravitational potential still goes as 1 over r, as in your Schwarzschild solution. And so the gravitational force will go as 1 over r square. So, as a matter of fact, Newton remains intact so far as the force is concerned. In Einstein gravity, Newton's law remains intact. It's still in inverse square law. So if you consider your Schwarzschild geometry, consider the radial motion of a particle, it will follow the same trajectory what the Newton is doing, because the force law is same as 1 over r square. So then the question very interesting thing comes about is that if that is the case, where does the self-interaction go? Yeah.
Can I ask, what about recession of Mercury?
Huh?
Recession of Mercury then?
Yeah, so answer yours. Exactly. So precession of Mercury does not require the change in the force law. It requires some change. And that is the subtle change what the Einstein theory provides. But that change is not in the force law. So we'll just see that. Yes, very good. So now let's. So before that, let's do it. Let us try to obtain your so-called Schwarzschild solution in our own simple-minded manner, where you don't have to solve this terrible non-linear differential equation. And we are more guided, so again, right in the beginning I said, I would like you to keep your robust common sense always alert. We only apply so let's follow the same common sense sort of thing. So we know, yes, the gravity has to be described by curvature of space-time, and we want to find out the field around the mass point, right? So mass point, that means it has a radial symmetry. So I should start with a spherically symmetric metric right? This is your to sphere part, radius, and I want a mass point which is static. So these functions A and B are functions of R alone. Now I say that first thing I want is my special relative, or which what we say, not even special, go even before that, and which we say, universality of space and time tells me that the velocity of light is constant. So velocity of light should be constant. So let us try to implement that here, right? You do your usual thing that, okay, you will write, and we are only considering, it's good enough for us to consider only the radial motion. Forget about this, it's not necessary for our argument. So what do you have? So your normal Lagrangian would be A T dot square minus B R dot square, where by dot I mean, so I will do both the things. It is some parameter d by d lambda for m equal to 0 particle, and it will be d over ds, the proper time for m not equal to 0. So right now when I'm talking about, I have a thing your this. Now you see the symmetry tells you metric is free of t, so I have an Et dot equal to constant. Let's call it E. Right? For massless particle, L is 0, so this is 0 equal to A times T dot is E square by A square minus B times R dot square. Right? And I am saying here dot is not restricted to the proper time but the parameter lambda. And concerning the massless particles. So this gives me R dot square equal to E square by AB, right? Or other way around. I squared by. I want that photons should experience no acceleration. So differentiate it once again. So what you get this is, we want this R double dot, which will be E square over AB dash, and this will be equal to 0. Right? Or what it meant was, the AB dash must be, this must be constant. And that constant I choose for to be 1 because asymptotically my matrix will become flat. So A and B should go to 1. So demanding, where is this? Yeah. So this demanding the velocity of light remains constant in vacuum around the mass point. This gives us that B is inverse of A. To determine all this, you require only these two functions, of which now one you have determined in terms of the other. Now you want the second thing. And two you want is that Newton's law should remain intact. Or essentially, or what you want to say, for the massive particle, m double dot is 0, I should get your, yeah, I should get r double dot equal to minus grad phi. Right? So you do the same thing. Same thing again you want. So what do I have? Now I in the Lagrangian. Oh, did I do something wrong? No, I did all right. So I have an AT dot square minus B is 1 over A R dot square. I know from here. Again, this is equal, that could be written as E square over A minus R dot square over A. Because for massive particle also, AT dot is constant, and you have some energy you define, and that you give. And the Lagrangian here is 1, for put time equal to 1. So what do you get this? You get that R dot square equal to E square minus A. Compute R double dot, and that will give you R double dot as minus grad phi. If I write, let's write A equal to 1 plus 2 phi. And that will give you the Newton's inverse law for phi equal to m by r. So you got phi as minus m over r. Isn't it a very natural and very straightforward direct way to get your Schwarzschild solution without having to solve any differential equation, except this stupid thing saying if the derivative of something vanishes, then the derivative, that quantity should be constant. We did nothing more than that.
Yeah. You can object that the A should be only, it's sufficient if A is only asymptotically equal to 1 plus 2 phi.
Pardon?
It's only asymptotically equal to 1 plus 2 phi in the limit of weak fields. From your argument, Newton must be equal in the limit of weak fields.
So. But I am saying the other way around. It is exact. So whatever is true, exact is true everywhere, asymptotically too. You know.
But how do you know it's exact if you don't put it into the Einstein equations?
What?
How do you know it's exact?
No. I'm saying this thing, R double dot equal to grade phi is exact. We got this. That's it. And and we have not done anything. We have just written A is a function of R, so I can write any function of R. I just split this into 1 plus 2 phi.
Yeah.
So this is it. Now, point what I am saying. So now I am saying is, okay, you do it this simple-minded little back of the envelope calculation, and you obtain this. And now say you verify it, that whether it satisfies Einstein equation or not. And the fun is that it does. So that is, so if it did not, then I wouldn't be talking about it. Anyway, there's nothing to say. So what again? So now here, what we were driven here by a simple common sense argument, and that is to say that look, the velocity of light should remain constant. So long as you are in vacuum, velocity of light should remain constant. So that is the one condition we implement. Nobody can have any objection to that. Second I am saying is this is the motion of the massive particle should include the Newtonian theory. So what he said is, I would have generally said, okay, this should come asymptotically, this should come to this. But my calculation shows you don't have to have this even asymptotic assumption. This is true everywhere. So this is another general physical principle. Whenever you are inventing a new theory, looking for a good new theory always includes the existing theory, at least in the first approximation. Because that is how science builds on. Science never says, because if it says that totally rejects something was earlier, that means there was something totally wrong with this, that was no science. Probably we did a bad science there. Otherwise, what you have is that new theory, that we have refined our framework. The whole thing changes only from the when the framework changed. Otherwise, there was nothing wrong with the Newtonian theory. Logically, all was perfect, fine. But now we enlarge that framework from space and time into space-time, and from that framework, the Newtonian theory must be included. And in addition, it will give you something more. And that something more should be. So here, this picture tells us that Newton is included in your Einstein. As a matter of fact, I have a simple note here in the archives, you can see it. Einstein is Newton with space curve. But this is a physically common sense is such an appealing approach that this. So whenever you are looking for some new solution, new things, try to first exhaust these direct, simple possibilities. And most often you might get the solution what you want. That these two physically motivated requirements lead us to the Schwarzschild solution, which is an exact solution of the equation. You might as well have asked, can I do the same thing for the rotating black hole, the rotating Kerr solution? The answer to that is yes. You could do that. So that's also it's there in the, except that what you in this picture is you have to start with an initial appropriate geometry. So here what you are saying is you have to start here. You start with a spherical symmetric geometry because the field is of a static point, mass point is spherically symmetric. When you want to have a Kerr metric, there you have to initially start with an axially symmetric metric. And in that axially symmetric metric, you introduce these arbitrary A and B. But you introduce A and B in the framework which already has an inbuilt axial symmetry. See? And then nothing more to be done, just implement these two things. That the photons experience no acceleration. No acceleration, I mean 3 accelerations. And massive particle experiences the grade 5. So again you can get your Kerr solution without solving the equations. Then of course next question you could say, so that paper is also on the archive, is this, that I have I have a rotating black hole solutions in higher dimensions. Given by Myers and Perry. And whenever you propose something, you will say, okay, it works here. Does it work in this more complicated situation? And the answer to that is, very recently, with some of my Iranian friends, we see that Myers-Perry metric could also be obtained following this thing. And that paper is in the archive, what they say, a novel way to rotating black hole metric in high dimension, and which is now soon going to come in that physical reality. So that's the picture here.
What about Reissner-Nordstrom metric?
And I was expecting something to come by, and that too will follow immediately to this. So carry on with your A and B as it is, the metric which I had, and first condition as it is. Light experiences no, your photon experiences no acceleration, and that gives you A as 1 over B. Now you want to explain the second thing. Now the second thing will be the thing is, again you will come, so let's, in this picture we come again up to this point, and A equals 1 plus 2 phi as it is. Right? Now I have to define phi. Right? Okay, so let us define phi. And we said every energy in any form must gravitate. Correct? So now when I put a charge on a particle, there is an electric field. So the electric field energy must also include. So for that, let us say that I want the potential pi at some value of r. So first let us say we start at infinity. The mass of the object will be m. Right? As you collapse down, then there will be an electric field energy here, so half E square, lying outside. Then when I want to put the gravitational, when I want to find the gravitational field energy here, this should be the energy for interior to R. So let us say this R naught I want to find for R less than equal to R naught times by the R. And you want the sign business of the minus. So I want to find out what is the energy contained inside this radius R. We started with M there. This is the energy which is lying now exterior to this, so I must subtract this M from this. From M, this quantity. And to subtract, to make this is the energy density, so what are you going to do? You have a, so this is something like half, you want this is integral from some R naught to infinity, E square, this will go as Q square by R fourth, Q by R square is, right? Then you have integral dr. Forget about you can take care of that 4 pi business. What you are going to get from this, that the energy which lies out, and you know this is the energy Q square over 2R naught, which is exterior to this. So when I am writing this potential, the energy contained inside this is M minus Q square by 2R. Sorry, 2 upon R. So let's make this R naught as a generic R at any value. So this is a potential. Oh, with the minus. And now you want that your grad phi, the phi here is identified by this minus n by Q square over 2R over R. And that gives you your Reissner-Nordstrom. So far as in the spherical symmetry, everything will work very well without no thing. Yeah. the same thing if you want me to do for, yeah, I think that will be bit, I have to be little, make some little more effort and to bring in the Kerr. No, sir, not Kerr. Kerr-Newman. The charge in with axial symmetry. There, this manipulation is so easy here because spherical symmetry. There it is not that easy. So there I have to do a little more jugglery around. And ultimately I will be able to convince you that that also works. But that's the picture you have. Okay. But yet, so here one thing you could have said this. Just imagine here. You should have asked this question. That look, at infinity the mass was m. Then he said as I collapse, right? There is the electric field energy. But as you collapse it, there is also the gravitational field energy. But we made no reference to the gravitational field energy. Or which other is self-interaction. That is their self-interaction. So if I take your, and this is that, so as a matter of fact, in the Schwarzschild thing also, you could have asked the same question. That when I wanted to say potential and wrote this as minus m over r, and you should have said, why did I write an m over r? Because the energy enclosed in the radius r should also take into account the gravitational field energy which is lying outside r. So I have an m to begin, but that doesn't happen. So that gives us a one very profound signal. And the profound signal is that gravitational energy does not interact through a force law. It interacts. So that's the next question I have to get to this. And this is very crucial. So there is a profound lesson here to say that the great phi is minus m over r rather than not like what you have going by the analogy with this thing, it could have been should have been like some m plus n squared over 2r over r. No. See, all that is to say, the gravitational field energy does not gravitate in the same manner as other non-gravitational energy. And yet, universality of gravity is there. Energy in any form must gravitate. It has to gravitate. And how it has to gravitate? So, first thing is gravitational energy does not gravitate through a potential. Whatever you want. It has no effect on the force law. It doesn't change the force law. This is very crucial to. And one simple argument could be this. Is this, that this is a secondary source. Mass point produces gravitational field, and this is the energy of the gravitational field. So it is a secondary source of gravity, not the primary source. So in your formal equations, you have this includes all non-gravitational. Now the question is, this secondary source, should it also sit here alongside the primary source which produces it? Which essentially is saying, should mother and the daughter be treated on the same footing? Now, this is not a very good argument, but formally that's one picture that you would say that you have. So, but then the question is, the secondary source, how does it operate? That's that. Again, before doing any rigorous mathematical argument, let's again do a purely common sense argument. So what you have Newton's law, universe square. Now in addition you want to take into account the self-interaction. So that's one of the driving motivations for general relativity. The Newtonian gravity cannot include self-interaction. And since gravity is universal, all kinds of energy in any form, must interact with gravitational. So, if you that's the question which you want. But then there is something very synthetic, something very physically meaningful and attractive about inverse square law. Because inverse square law reflects the conservation of flux. So it's a conservation law. It's a conservation of energy. That's what gives rise to the conservation of charge for the electron. So there is something very sanctified about inverse square law. So even when I am seeking a new theory of gravity, this beautiful feature involving the conservation of flux, I cannot give up. I should always respect it. So that should always be. So inverse square law should remain intact. So that's the picture it tells me. Now then is, where is the possibility of accommodating self-interaction? The only possibility then possible comes about is you see how we expanded your framework to include the zero mass particle. We expanded the framework from space and time to space-time, bound them together. And the motion of zero mass particle automatically got included in the new framework. Now we have come that we want to include the self-interaction. And we have also seen that the gravity is to be described by the curvature of space-time. So we are again enlarging the framework from flat space to curved space. And in the process, we include the Newton, but something else we did, and something else that should come by asking the space to be curved. So the enlargement of the framework is from flat to the curved. Now when the space gets curved, what should it incorporate? It should incorporate something which is not incorporated in the Newtonian theory. And what is not incorporated in Newtonian theory is the self-interaction. So the self-interaction is the source for curving the space. So the self-interaction, so this self-interaction, it does not interact through a potential to modify your law of gravity, it interacts through curvature of space. And that is, where did I say something? It's not there here now, is it? So that is what gives to think that Einstein is really Newton with space curve. So the curvature of the space that takes into account, takes care of your self-interaction contribution, and keeping that Newton's inverse law intact. So that is, isn't it beautiful? That new thing you want. So first thing is, yes, now the result comes. Then how is it that all this I am talking, this nonsense I am talking, but no textbook talks about? Simply because I say this is sitting in the space curvature, but space and time are bound together. So in Einstein's equation, I have the curvature of space-time. So space curvature is already sitting in there, right? So your self-interaction got automatically incorporated without you knowing it. And yes, so and that's why you don't see any specific discussion. But let me make this thing slightly explicitly clear. So that is, so you have your So let's look at this. At the Einstein's equation for a spherical symmetric space-time. So you have our good old metric. You have a dt square minus bdr square minus r square d omega square angular part. Right? Then you have RTT here, RR here. And so let's say R theta theta, which is same as R phi phi, equal. This is what we have. And we want to solve this thing, all this being equal to 0. So first simple thing which comes about this. So you want this to be 0. Since these are the zeros, I can as well ask first, how about this? And this gives me since each one should vanish, so this should also be 0. So that gives you AB equal to constant equal to 1, demanding asymptotic flatness. So this is what you. Now, with this, if you put in here, and let's write as used earlier, A as 1 plus 2 phi, then RTT equal to 0, or the RTT will become something like minus del square phi, that equal to 0, and your R theta theta will become something like plus minus maybe, right? Some 2 over R square R phi dash. Again, I am giving you a trick that nowhere you have to solve a nonlinear equation. Not only nonlinear, you don't even solve the second order equation. You solve a trivial first order equation. And so, putting A equal to your RTT equal to RRR reduces, so this will, let's not bother about it, you don't need to really have this. This equal to 0 gives you phi equal to minus m over r. And of course, this tree will solve this equation. So this is the most direct way to obtain the Schwarzschild solution, where you don't have to solve the second order. As a matter of fact, what I'm saying, let's think that this relation thing, what in general could be said is for any spherical symmetric or even the symmetry with a nut parameter, there is a general relation. You will have something of the kind. Is that right? Probably I should write in terms something like this. Z theta theta will be equal to DDR. Well, some factors forget about of G RR plus GRR. And this is what one is. So, this is, I'm saying it is in general, not only in spherical symmetry, but and with a nut symmetry as well. So what you say is, one is an first integral of the other, so you don't have to solve. And once I have this with me, and of course here we started with your GPT equal to GRR, and then as here, this becomes a linear equation. And you solve this, and this gets trivially solved. Okay, so that's the picture. Now let me have, yes, now it's
one question about the solution of the equation. You have the nabla squared pi is equal to 0.
No.
You say this is solved by 1 over r.
Yeah.
M over r. Sure not.
No.
I am always bothered that this means you actually have delta function at r equals 0.
Yeah, of course.
So it's you cannot really say it's a solution which has which is tends to 0 everywhere, but outside it's not 0 everywhere. So
it's not 0 everywhere.
It's not defined really at origin. So
that's right.
So I wouldn't call it in that sense vacuum solution.
It's a vacuum solution.
Is it?
It is a vacuum solution.
But if you have like point charge, in electrostatics, then you have delta source, and you don't say it is vacuum solution. It's just one charge solution.
Yeah, so that's the same.
It's the same.
Same, that's you have to. So here is also the vacuum solution. Yeah. That's right.
But it's not vacuum.
Huh?
In electrodynamics, it's not vacuum.
Why it's
well, because we have one charge.
But here also the point particle.
So okay.
Yes, the particle is sitting at your delta r equal to 0. Yeah.
Right.
Yeah, that's it. It's exactly the same. So
same,
it's here there is no difference. This is a good old classical theory. There's no
vacuum probably means external solution.
Huh? It's external solution, of course.
That is the meaning of vacuum probably, no?
Yeah.
But it refers to external case.
Yeah. So it is so.
Because inside you have a matter.
So however you put your mass point, whether it is a delta function, whether it is a finite extent, it is exterior to that. So that's what we call this in the Schwarzschild exterior solution. It's a vacuum solution.
Okay.
Yeah, but there is. So you got this. But so far I have not brought this. Where has that self-interaction gone? So now for that let us do a trick. And that's what you should ask. That why did I demand the self-interaction should be this kind of thing? That it should be some del square phi going at phi dash square, right? Going with the same analogy as the density, energy density of the gravitational field will go as phi dash square, like half E square for the electric field. So what you would say is, in vacuum, I should really be solving this equation, and this is what is the self-interaction. And why I don't see this happening. So, not that I don't see it, to see it explicitly. Now, this is our expectation. This is what you expect if space is flat. This does not take into account the space being curved. So this is for relative to the flat space. This is what you would say. So now let me ask the same question. Let me say, let the space be flat. And by that I would mean is, let me set B equal to 1 in the metric upper. If you make B equal to 1 in the metric above, then you will see, of course, B equal to 1, then you will see your RTT zero equation will have things like del square phi going as phi dash square. So you will, so what does it mean? It meant that the self-interaction went into curving the three space. So that is, so it is, so what, so the self-interaction interacts more subtly, and that subtle interaction is, it interacts through enlarging the framework by making the space flat to curve and keeping the so you said the Newtonian potential is sitting here. The grad phi comes from here. So this you keep intact. Self-interaction and it comes from here. So what we should say, self-interaction does not produce grad phi, but instead it curves space. By space I mean the curves three space. So the source of curvature of three space is the self-interaction. And this picture, this does not does not become explicit unless you really want to seek for it by making the space part flat and then look at the time component of the Ricky tensor. So that roughly speaking, what would you say is the self-interaction produces B, Newtonian gravity produces A. So A is grad phi follows from the GTT and this. And of course, to keep the velocity of light constant, the two have to be related and there should be inverse of each other. Now the final statement to say this. With this, what do you have? Oh, no, this I need. Let me make a final statement here. When you come from Newton to Einstein, there are two new things you have to incorporate. One, light must feel gravity. through the self-interaction. For light to feel gravity, space must be curved. Right? The only way light can feel gravity, the space must be curved. And this is precisely what the self-interaction does. So, the self-interaction precisely does this. The self-interaction produces the curvature in space, curves the space, and that to facilitate light to feel gravity, to facilitate photons to feel gravity. So the two new things which we have to incorporate are so beautifully takes care of each other. The space curves requirement by light, it is produced by the self-interaction. And that is why the Newton's law remains intact. You don't have a... So this is a really sublime elegance, that two new things to be incorporated and they beautifully incorporate each other, keeping the basic gravitational law intact. So that's the sublime beauty. But it's not for nothing that Dirac called general relativity as the greatest feat of human thought. This elegance, actually the personification, crystallization of elegance, you don't see in any other theory that you have. So that's me. But there is something more to this. So now the next statement, next thing I would like to do. So here we saw the self-interaction does not gravitate through a stress tensor. It gravitates through enlarging the framework, making the space curve, right? And the self-interaction is a secondary effect. So from this I want to make a general principle. All secondary source by framework enlargement and not through a stress tensor. So this prompts us to propose this kind of a general principle that if the source, which has no independent existence of its own, it is produced by some primary source, it's a secondary source, then it must gravitate by enlarging the framework rather than modifying the force law, which will be writing a stress tensor on the right hand side of the Einstein equation. So, to incorporate self-interaction, we wrote no stress tensor for self-interaction on the right. And this I would like to promote to a general principle that this should happen for all secondary sources. And in particular, for the so-called vacuum energy. Now, is there still some time to go, or is what the time like?
It's 11:45.
11:45. Then probably we should take up some questions and some discussion rather than, because that vacuum energy, I want you all to be fresh and bouncing back on me.
Any questions?
I have only a comment.
Yes.
I heard one different argument about how to derive Einstein equations, but it's very similar in spirit. It's like field theoretical. You start with spin 2 fields in
Yes.
symmetric tensor field, but free, so linear and without any interactions. And you couple it to the only source which is symmetric, that's the T mu nu.
Yeah.
Very natural source. And then you derive equation of motion for that field. And that equation of motion will look very similar to the equation of motion for gravitational waves, basically. It will be almost equivalent. But then you would say, okay, so on the right hand side, I'm missing I have T mu nu of the other fields, but I'm missing T mu nu of my spin 2 field.
Yeah.
Right. So I make like next step when I am introducing new Lagrangian, which will have the original spin 2 field plus terms which would generate this additional T mu nu on the right hand side of equation of motion. And then I will derive new equation. It will be now nonlinear, more complicated. But you would say, okay, but I'm still missing on the right hand something, which is the T mu nu of this new field.
Yeah.
Which is so because its T mu nu is now much more complicated than before. So and you will, if you do it infinitely many times, you will iterate it. You will end up with Einstein equations.
Well, yeah.
Well,
that's how our darling of everybody, Feynman, seems to have done it.
Yeah.
That's the famous Feynman's, and from a field theoretical point of view, he will say, of course, Feynman was never known to be modest. That's the only way you could do it. And I would say, no, this is the only way you could do it. You can't do it. Nothing could be simpler than this. So that's precisely a good point.
But it exactly shows that the self-interaction in the Einstein equation comes from including the T mu nu of the
absolutely, it's including the things. But when you finally include, it disappears.
Yes, that's
very fun. So now, at the point what at that time when the writing it occurred to me, I forgot. So what really happens is this thing here. In Einstein equation, what happens is this stupid phi square here is brought on the left hand side.
Yeah.
So it is sitting there. So that, and we say it's a nonlinearity. It's the nonlinearity of this. The self-interaction creates a nonlinearity, but then it becomes invisible to me. So this is to make it visible. It's not. So I'm saying that I'm not giving. It's nothing very profound, but it is profound in the sense of understanding the thing. That this is where the self-interaction is really sitting.
Maybe I will have a more technical question. So you said it's a similar technique without derivation of without solving Einstein equation, you can even derive this Kerr metric. But and it highly dependent on how you choose this ansatz, right? The initial metric, and probably it should be axially symmetric.
Yes,
definitely. But this is not the only. I mean, you can generate axial symmetry not only by rotation, and it can be just some more extended object or.
No. So sorry.
So how,
No.
How you create this rotation?
No. What do you want? You want a solution for a rotating object?
Yes.
Right? So you should then take up the axial symmetry which is generated by rotation. So it is not a statement that this is true for any axial symmetry. So you have to take an appropriate.
This is probably a very complicated part. I mean, how can you know the effect of rotation in advance?
Oh, no, even very much. You take essentially. So what you have your. So first start with the three-space geometry. And if you have an axial symmetry geometry, three-space geometry is just spheroidal. You write the symmetry for a spheroid. And then to that, to make it force-step, add a dt square. And then you find the metric which you get is the same, the Kerr metric with m equal to 0. So that's the way it comes. So if you see our paper, you have that you start with a spheroidal metric for a not spheroidal, it's ellipsoidal. That you need a geometry. Add a dt square to make it 4-dimensional. Then make a coordinate transformation, and that metric would actually have this form. Your usual Born-Twist form you could have, and that's the d square and dt. Where rho square is r square plus a square cosecant. This is the flat metric. And you have the ellipsoidal metric, add a dt square to this, do the coordinate transformation, you come to this. This is the metric with the m equal to 0 in the curve. And now here you add this. The only place where the potential, you add a function f(r) if you want, and add a function gr here. And then implement the two conditions. The photon acceleration is 0, and so here take a radial axial motion, simplest of thing, just to determine this. And that will determine f should be equal, f and g should be equal, and there will be 2mr.
Beautiful how you remember this question. Very nice.
You say for I'm triple your age. So for many, some of them, not all of you. This is what you have been doing in your life. So not in that.
Any other questions? Okay. If not, thank you very much.